Thanks a lot. I'm presenting joint work with Cornelius, Fritz, and Michael Schweinberge, and Angelo, who's actually also here in the room and volunteered to take any difficult and complicated questions that I can't answer at the end. And the paper that I'm presenting is a strategic model of software dependency networks. And the motivation for the paper really goes back to this idea of vulnerabilities in software networks. So one particularly important example is the heartbeat bug. It was a bug that affected the OpenSSL protocol, which underpins a lot of the crucial communication between any kind of computers on the internet. There was a small vulnerability in it that rendered all the web servers that used this software vulnerable themselves. The consequences of this were really quite widespread, and it resulted from this idea that software today is now a collaborative effort. You don't build your software on your own. You don't just sit in your basement, code away, build everything yourself. Rather, you reuse existing software. These sophisticated repositories, they make use of existing software libraries, which is good because it increases your efficiency, but it also increases as heartbeat. And there's a whole database from the NIST that shows sort of the prevalence of vulnerabilities and how they propagate. So the con is it increases the risk that a bug in one library or one software package actually affects a large number of other packages. And this is quite important in practice. So the cost of software failures is estimated in 2018 to be around $1 trillion US. So this is like really first order kind of problem. And there's surprisingly little work on the economics of these linking decisions and sort of trying to bring a bit of strategic behavior into this kind of setup. And that's exactly what our paper is doing. So we model a software maintainer's decision to form these dependencies. We then analyze the equilibrium network of these dependencies. We do an empirical analysis, which is not that straightforward because the networks that we are considering are large. So in our case, we look at the Rust programming language, which is sort of large and important because it's used for many security relevant applications, but it's not so large that we can't handle it anymore. So it's on this very nice intersection of important and doable. So even for that, we have to provide a new scalable algorithm to estimate these kind of network formation models empirically and at scale. And then we use this to provide an analysis of systemic risk, identifying those packages where vulnerabilities will actually propagate most to the rest of the network, to help policymakers and software developers identify packages that are in dire need of protection and sort of make extra efforts to make sure that they don't have bugs. All right. So what we find is when we study the model, we find that there's evidence for externality in linking decisions, where my decision to link to another package does not take into account the additional risk that this package's links and dependencies has on those packages that depend on me. And the result is that there's excessive connectivity in the system. And we then explore what this means for, I would call it systemic risk, but you can think of it in a sort of propagation of vulnerabilities kind of sense. All right, there's as I said, there's surprisingly little that has been done on this intersection on each part or in each aspect of this. There's a lot of work on it's under the label of dependency graphs for those of you from CS. In economics, there's lots of work on strategic models of network formation, but they haven't been applied to this kind of setting yet. And in part, it's because it's a hard problem computationally, as you see as I go along. All right, so let me tell you a little bit about the data that we are using. So we look at dependency graphs, and the dependency graph arises between different software packages, where a function, a method, a module, a library in one package uses a function or a method in another package. Whenever that's the case, the functionality of the linking package depends on the functionality of the linked package. These packages can be identified by their name and then a number. And we aggregate all of this together on the repository level. So repositories combine several packages. You can also look at it at the package level. There's we can talk offline about why it makes more sense to do it at the repository level, I think. But basically on the repository level, there's a maintainer for this repository, some coder who takes a decision about whether to implement the code themselves or to just use whatever is out there. And there's this paradigm, don't reinvent the wheel, just reuse existing software. All right, so from other repositories. But this reuse creates links between different repositories, and we've created this network based on the dependency graph on the package level, aggregated onto the repository level, because it's a more meaningful level of aggregation, I think. So the dependency graph that we have is the network of repositories and their dependencies. We get the data from libraries.io, which is very nice because there's prepared a couple of things, made life a little easier. As I said, we focus on Rust. There's about 35,000 packages in the Rust. It's called Cargo, the package manager of the Rust software ecosystem. And there's about 696,000 dependencies between those nodes. We have a couple of covariates that we're going to use in the estimation. We have the maturity of each package, when was it first released, so the time since that first release. We know how popular it is by looking at on GitHub, how many stars has it received on GitHub, and we know how large it is. So it gives us a couple of covariates that we are going to use in our estimation. And what you can do is you can really create this graph of dependencies. And what we've done here is we've just taken this graph and we've looked a little bit at communities in this network, try to find the right number of how many communities are there, because it's going to be a parameter in our estimation algorithm later. All right, so one thing that I just want to leave you with on the network statistics is that there's significant heterogeneity. So there is some packages that have 15,000 other packages depending on them. Half of the ecosystem almost depends on that most interconnected package. And then there's packages, like most of those packages have no other package depending on them, right? So there's significant heterogeneity in this system. And when you look at what are these packages, so we did a little bit of a sanity check, it tends to be those that you think it is. So libc, rand, log, these are packages that are sort of infrastructure kind of packages used in whatever kind of software development you do in Rust. Usually, it's likely that you're going to use one of those. In particular, libc is just used a lot. All right, so that's the data. Let me tell you a bit about the model. What we want to do is we want to estimate a structural model of network formation where we have one observation, which is the one network. So we're not looking at in any sort of time evolution of the network. We just take the last snapshot and they say that's the network. We have the list of repositories, we have our observables, but we also want to use unobserved heterogeneity. So we introduce what we call types, ZI. These types are a bit abstract. The way that we think about them is that there's something unobserved in sort of different software packages, and you can cluster them together. You can group them into meaningful groups based on unobserved things. And the question that we have to answer is how many of those are there, which is why we did this community detection in the beginning to get some rough estimate. But it's a parameter that we plug in. How many of those unobserved types do we have? I think of them as sort of like a type of a package or of a repository. Could be that it's an operating system component, or it's a web server, or it's a text processor. These are really very different kinds of software with very different functionality that they need. And therefore, to me, it makes sense to group along those dimensions, but don't think about it too literally in that sense, right? These are just sort of groups of packages that are clustered together, which we use for unobservable heterogeneity. So these repositories, and their dependencies, they form a network, which is this matrix, and it's directed. So that's something that we add to the literature. It's a directed network of dependencies between packages. And one way to think about the sort of strategic modeling here is to say, well, there's two maintainers, 1 and 2. Maintainer 1 needs to take a decision about whether to link to package 2, and there's sort of a baseline model, which is the stochastic block model, where you can say, well, if you group according to this unobserved heterogeneity, and you just want to figure out should I link or not, then what you do is you basically take into account the benefit of linking, which is the cost you save on implementing this yourself, with the risk of linking to a buggy package that might make your package vulnerable. So that's this this direct utility basically that you're weighing. And in our model, what we add on top of that is that we then say, well, you know, in this realistic network, you have all these other dependencies where package 2 depends on a bunch of other packages. And then there's all those packages that depend on package 1. And when the maintainer of package 1 makes a decision to link, they don't take into account the effect of these links from like to all the blue packages onto the orange packages. All right, so that's the basic model. So you can write down the utility for this. It looks a little different from the stochastic block model. So you write down the utility, and you then do the standard thing that you do in these network formation models. You say, well, you know, we think about it in a sort of abstract way, that there is an update decision that has to be taken, and the link is where you randomly select the link. The link is maintained whenever the utility of doing so is higher than the utility of not doing so. And this evolves in sort of a Markovian way. You just test this one link at a time. So what you do what you end up with is you end up with this network of all the dependencies where, you know, there's an equilibrium, but it's computationally quite tricky to do. So we have to do a couple of things for tractability. The main assumption, the main technical assumption that we do is that the externality, or basically the coefficient here, that this term, the indirect costs and benefits or risks from me linking to others, and those that I impose on others are the same. So that is a necessary condition for the estimation that we do. Again, something that we're happy to discuss if you're interested in why we do it this way. So what we really need to do in this estimation is we need to find this equilibrium likelihood, which has a component within types and between types. So since it's a stochastic block model, most of the links will be within types. There's some between types, which is, you know, the deviation from the pure stochastic block model, but that's just how the data looks like. And the real tricky part here is this normalizing constant in the within type estimation for the likelihood. So that's because of the number of possible configurations you can have in this exponential random graph model that we're using. That makes it a little difficult to estimate. So what we have to do is we have to approximate this estimation, and there's a two-step procedure that we're developing in the paper. Where in the first step we find the number and the allocation of these unobserved types using variational approximations and a minorization maximization. And then once we have that, we plug this into the approximate likelihood estimation using either a maximum pseudo likelihood or contrastive divergence. And that gives us the likelihood at the end. We've built an R package that does this estimation for directed networks. Previously, you could only do it for undirected networks, so there's a bit of a contribution here. And I think it's super useful to have that package because there's many interesting systems that you can study that are so large that nobody has studied them before. All right, so the empirical results, there's really one table that I want to show you, which is this. Once we do this estimation, we find that indeed there is this externality, statistically significant. It's large and positive in the linking decision. This is this interpretation that the network is over-connected. We also find that the size of this externality goes down as the block size increases. And the largest block in this system is a block of, I would call, any other business kind of software, things that you can't really group. So we looked into what these packages are, but I don't find a pattern between them. So this is the largest, and then within those, there's less of an externality. There's some stories you can tell about of the covariates. That's why we've included them. But just in the interest of time, I want to go and just show you one thing, which is about the contagion, right? So in these networks, right, when there's a vulnerability in one package, it renders this package susceptible to an attack, and all the packages that use it are potentially also susceptible to an attack. So that very much has a spirit and a flavor of an SIR model of contagion, right? It's not exactly that, and we can talk about the differences, but basically it means that there's a package that is susceptible to an attack that could be infected. If it's infected, it infects everybody that connects with it. Once it's fixed, once it's debugged, it can be recovered. So what we look at is what's sort of called the K-step systemicness. It's the number of downstream packages K steps away, so K steps of dependencies away, that a repository I affects in this directed network. Let me just sort of, yeah, so basically if you look at the repositories with the highest in degree, you can see sort of how many packages they would affect if they had a vulnerability like 2, 3, 4, 5 steps away. And you can, based on this, you can start identifying those that you really need to protect. So it turns out that the literature on in epidemiology has done a little bit of how do we protect populations in a network when there is a disease going around. COVID has sort of triggered this kind of research. There's a bit of a heuristic that you can use on which nodes you should protect. And what we've shown here is the test of what happens if no node is protected. So there's no protection, and we take sort of insolvency, or we take the vulnerabilities of 50 packages. You don't protect anything, and then you go 2 steps, 3 steps, 4 steps away. That's the black line. The dashed blue line is what happens, how would that look like, this process, if we were to protect, based on this heuristic, the 10 most systemic nodes in the system. And if this is sort of better than, like if there's an improvement, if the slope goes down as you protect more and more and as you go along, it tells you that this heuristic actually works in protecting these this system. So we can show that even if you protect only a relatively small number of packages, 2, 3 steps away, you actually prevent large parts of this contagion process from happening, which is quite nice. So I think I have like 30 seconds or so left. So let me just say what we do in the paper is we build this network formation model for dependency graphs of software packages. We treat maintainers as, you know, strategic agents taking a decision on how to link. We then estimate this network using a realistic programming language, and we show what you can do in order to protect this ecosystem from vulnerabilities. There's a couple of things that we have on our plate to do. So like fixing the number of these unobserved types, that's something that's not so straightforward, and that affects the results in a bit. So we have to choose this in a disciplined way. We're currently working on some counterfactuals, because that's the real meat at the end. If you can change the parameters of the model in this estimation, and then look at how contagion would look like, we can think about policies, how to protect these systems beyond making it impossible to, you know, have a vulnerability in libc and packages like this. So with that, I'm at an end. I'm looking forward to any and all comments. Yeah, Martin.
So what does protection mean in this context?
That there's no vulnerability.
Somehow you...
So you can think of it in the following way. Like some vulnerabilities occur because you don't do a type check when you input a variable, and that can lead to overflows. That can lead to sort of the server that runs the website that has this vulnerability, for example, to be exploited. So one way of protecting them is to add lots of checks to make sure that this kind of bug doesn't occur. And you would have, this is a hypothetical setting where you would have to do this for all kinds of bugs, which I know is impossible, but it gives you sort of a benchmark.